Hello everyone. Today we will be talking about the extraction of a natural product, which in our case is limonene. Let's start by talking about a process that you're probably more familiar with, the decaffeination of coffee. A typical cup of coffee will contain somewhere between 70 to 140 milligrams of caffeine. So in order to remove this caffeine, three main methods can be done. One is solvent decaffeination. This is going to use a solvent like methylene chloride or ethyl acetate in order to extract the caffeine from the coffee beans. So in order to do this, the coffee beans are steamed and then soaked in solvent to remove the caffeine, and then they will be dried and roasted afterwards. Then there's carbon dioxide decaffeination. This is also going to remove the caffeine, but may also remove flavor compounds because carbon dioxide is more selective. This is done at high pressures so that the carbon dioxide can dissolve the caffeine, and then the caffeine will be removed from the carbon dioxide with water. The last one is water decaffeination. This is also called Swiss water decaffeination, and it's done by soaking the beans in hot water to remove the caffeine and flavor compounds. And then the caffeine is removed from the water by filtration, but the flavor compounds will remain. Previously, essential oils and other chemicals derived from natural resources were extracted from plants using hydrocarbon-based solvents like hexanes or halogenated solvents like methylene chloride. Hexanes is a highly flammable liquid and vapor. It is also toxic to aquatic life with long-lasting effects. These solvents exhibit human toxicity and are hazardous for the environment and require a lot of energy to produce. Also, the removal of these solvents requires a lot of energy as well. Additionally, methylene chloride, also known as dichloromethane, has been banned by the EPA due to its harmful effects on humans and the environment. In order to move away from these harmful solvents, our experiment today is going to focus on green chemistry, which involves the designing of chemical processes that minimize the use and generation of hazardous chemicals. For this, we'll be using carbon dioxide, and that's because it has been promoted as a green solvent, because it has very few health risks, and it's both cheap and energy efficient to produce. We will be using liquid carbon dioxide, because it is a good solvent to extract limonene from an orange peel. It's fairly easy to produce from dry ice, and the liquid will boil away at room temperature as soon as the extraction vessel is depressurized. There are a few alternate methods of extracting limonene. One is a steam distillation, which we see here. This involves boiling orange peels in water and then distilling the resulting oil in a steam at a temperature below limonene's boiling point. The limonene can be separated from the water because it's not soluble in water and will appear as an oily layer on top. Then there's a sock slit extraction, which is seen here on the right. This involves filling a fiber thimble with orange zest and then using isopropyl acetate as the extraction solvent. Then there is cold pressing. This can be used to extract the limonene from orange peels as well by heating them up in hot water and then pressing the oil out of them. The last is organic solvents, and this can be used to extract the limonene because it's hydrophobic, which is going to reduce the amount of heat and energy required compared to water-based extractions. In this case, you would allow the orange peels to sit in a solvent like isopropanol or ethanol in order to pull the oil out of that. All of these methods are considered to be less green than the method that we will be doing today. This is because a lot of energy is required in order to extract the limonene out. Even in the case of organic solvents, where there's less energy required, you are then using an organic solvent which is considered to be less green than things like water. You are probably more familiar with carbon dioxide as a gas. However, at -78 degrees Celsius, it can exist as a solid. This is known as dry ice, and you will be working with it today. Carbon dioxide exhibits unique properties because at -78, it can also sublimate and turn directly back into a gas. So, how are we going to get liquid carbon dioxide? Well, we will be taking our solid carbon dioxide, dry ice, and adding it into a centrifuge tube. The cap will be tightened, and the centrifuge tube will be placed in a warm water bath. This will allow the dry ice to sublimate, pressure will form in the tube, and then it will be able to turn into a liquid by this little bit of pressure that we have generated, as well as the warm water surrounding. This is going to happen approximately around 0 degrees Celsius. Limonene is a colorless terpene that is found in various citrus fruits and has a relative molecular weight of 136.236 grams per mole. It possesses a chiral center, which causes it to exist as two enantiomers. S-limonene, seen here, has the characteristic odor of a lemon, where R-limonene has the characteristic odor of an orange. Today we will be extracting R-limonene. Not only is limonene a flavoring agent, but it also possesses anti-cancer, anti-inflammatory, and immunomodulatory activities. In order to liquefy the carbon dioxide, a lot of pressure will generate in the centrifuge tube to reach that supercritical point. Because of this, no glass containers may be used during this experiment for your safety. You should also use gloves when handling the dry ice, as it is much colder than the regular ice that you're used to. Additionally, don't liquefy the carbon dioxide more than 5 times in the same centrifuge tube because the seals will go bad. You'll begin today's procedure by weighing an empty centrifuge tube. Then you'll place a coil of copper wire into that centrifuge tube at the bottom and weigh the mass, as seen here in Figure A. Then you'll add about 2.5 grams of finely grated orange peel and determine the exact mass of orange peel in the tube, as seen here in Figure B. Then you'll fill the rest of the tube up with crushed dry ice and put the cap on until it stops turning, as seen in Figure C. There are 2 very important notes here. 1, when you're handling dry ice, make sure you're extremely careful. In order to crush the dry ice, you can either grind it up with a mortar and pestle, or you can put it in a paper towel and smack it with a hammer. Also, whenever you're putting the cap on, make sure you do not over-tighten it, because this will damage the seal. You also want to make sure it's tight enough though, otherwise your carbon dioxide will escape. Then you should place your centrifuge tube in a plastic cylinder filled with warm tap water. Plastic beakers will be provided for you today. Do not use any glass containers for your safety. You will then submerge the tube into water to see if it's leaking. If you see a lot of rapid bubbling, you need to remove the tube and try to either tighten the cap or replace it with a cap from a different tube. With the tube submerged in the warm tap water, pressure will begin to build up. This is necessary in order for the carbon dioxide to reach the supercritical point, allowing it to become a liquid. After a few minutes, all of the carbon dioxide will be gone, and you'll be left with a small amount of oil at the bottom of the tube. You can repeat this process again by adding more dry ice in order to extract more oil. After, you should have a noticeable amount of oil in the bottom of your centrifuge tube. You can then remove the copper wire and the orange peel and reweigh the centrifuge tube to determine the mass of the limonene that you have extracted. You can then analyze the IR spectra of limonene. Please see the additional video for information about infrared spectroscopy and how to analyze it.